track moving?
Yes.
Okay, if you're on the same track, then let's continue. We told people from the start of this session that if you want to do chemistry equation, full balanced equation, you must now to come up with it. You have seen how far it has gone. Everywhere you go, equation of reaction, equation of reaction. So if you cannot write equation of reaction, then you look for ways of getting it. Otherwise, it's going to be harsh. So here we are having another example that says 48 cubic centimeters of methane. Who knows the formula of methane? Methane is an organic compound. It falls under which group? Methane. ANE. ANE is what? Organic chemistry. People never did organic. Yes?
We did.
We did. So if something has ANE,
Yes.
it is under which hydrocarbon? It is an what? Alkane, isn't it? Hmm?
Yeah.
If it has ENE, it is what? Alkenes. People have forgotten. Hey, people have forgotten chemistry. I've seen. So
Teacher, I can't see clearly what you're writing.
I'm going to zoom it. Is it clear now?
Yes.
Okay.
Okay, sir.
Yes.
Good. So here, if you burn any organic compound in the air, what is the end product? When you burn organic compounds, what is the end product in the air? In air, the end product is carbon dioxide and what? What?
Water.
Water. So any organic compound, if they say methane, me is how many carbon atoms? 1. If it is an alkane, it is CH4 because carbon has a possibility of bonding with 4 other atoms. Okay, so methane is CH4 in the presence of oxygen. The end product is carbon dioxide and what? Water. What follows next is to write the states. Gas. This is a gas. This is water. Is it a gas?
Yes.
Yeah.
Now, after that, what follows? Balancing the what? The equation. Is that equation balanced? Because here I see 2 oxygens, here I see 3. Here I see 2 hydrogens, I see how many? 4. So what should I do? Actually, the problem is with hydrogen and oxygen, isn't it?
Yes.
Carbon is okay.
You add that two on the water.
Water. And then these are 2 oxygens, okay? And then 4 hydrogens.
4 hydrogen.
So this one is fully balanced. Now, the next question is, what does the question need? Go back and read. 48 cubic centimeters of methane was exploded with 212 of oxygen at a certain temperature and pressure. The mixture was then cooled and allowed to attain room temperature and pressure. Determine the volume of each of the remaining gases.
Teacher.
Yes.
Teacher, the equation is not okay.
Why?
On
Sorry.
this.
Sorry. We have 2 oxygens and then we have the other 2 here.
Yes, teacher.
So to make 4. Thank you for being
Thanks for your correct.
observant. Now here they are saying 48 of methane was exploded with 212 cubic centimeters of oxygen. They are telling us to determine the volume of each of the remaining gases. If you explode this and this, the whole of methane will burn. The end product will be carbon dioxide and what?
Water.
Water. All these elements are in a gaseous state, and this one will remain unused because it will go away. Even the water in this vapor at gaseous state will remain a gas and to remain unused. Is it used?
No.
These are the end products of burning. So this one will remain unused, even this one will remain unused. Okay? So you have to look for the volume of this one, and then you also have to look for the volume of this one, and then also you have to look for the volume of oxygen, because they have given you a certain volume of oxygen which you don't know that 48 of this one can explode with. You get? So if you consider volumes, we shall say, let's start with oxygen and check if the volume of oxygen they have given us was all used up. Okay? They are telling us that 1 volume of methane reacts with how many volumes of oxygen? 2 volumes of oxygen. Now, the question comes, they have used 48 volumes of methane.
Pardon, teacher.
Yes? Do you see the equation that is there? Yes? We are using Gay-Lussac's law. He considered volumes and they do so in simple ratios. So we are saying from here, 1 volume of methane reacts with 2 volumes of oxygen. 2 volumes of oxygen, isn't it? So what about the volume of methane given? What volume of oxygen does it react with? So the volume of methane is 48 cubic centimeters of methane reacts with 2 times 48. 2 times 48 cubic centimeters of oxygen. This one we are doing to check if the exact volume of methane used all the volume of oxygen given, because we're given 212 volumes or cubic centimeters of oxygen. So we are using this 48 to know certain that whether the methane burnt with all the oxygen given. So here we find out that 2 times 48, you get what?
96.
96. Was all the oxygen used?
No.
No. So that is the volume they want. They are saying determine the volume of the remaining gases.
That is
So what was the volume of oxygen left?
116.
It becomes 212 minus 96 cubic centimeters. So the difference is 116 cubic centimeters of oxygen unused.
Teacher.
Yes.
Teacher, where does the 48 on the oxygen come from? I thought the 48 centimeter cubed was for the methane. Now where did the 48 of the volume of oxygen come from? Where you multiplied 2 times 48? I didn't understand there.
Okay. Maya. Maya. Maya, please come back. Unmute.
Yes, teacher.
Good. You are the one asking the question, isn't it?
Yes.
Now, they told you that 48 cubic centimeters of methane was exploded with 212 of oxygen. Yes? So you wanted us to use this volume of oxygen. This guy Lussac said he studied the behavior of gases. Just they do so in a simple volume ratio. They obey a simple volume ratio. Now, from the equation of reaction, we have found out that 1 volume of methane reacts with 2 volumes of oxygen. Do you see that?
Yes.
From our equation? Now, they have told you that only 48 cubic centimeters of methane, it reacts with what according to the equation? It becomes 48 of methane times this. You want to know the exact volume of oxygen that was used. You get it?
Yes.
So the exact volume of oxygen used was 2 times 48, the one of methane. From the simple ratio we have, it is 1 times 1 by 2. So oxygen use twice of the oxygen, use this volume of oxygen, that is twice the volume of methane used. So if you have the volume of methane, use it to find the exact volume of oxygen that was used. Okay? But
Yes.
in the equation, this was the total volume of oxygen that was provided. It was 212 cubic centimeters. Now, this indicates that a certain volume of oxygen was not used. And that's why the question is determine the volume of the remaining gases. Is it clear?
Yeah.
So here, that's why we say, if you want the volume of the oxygen unused, volume of the oxygen unused, we say it's going to be the volume of oxygen, total volume of oxygen that was there, total volume of oxygen minus the oxygen that was used in the experiment, oxygen used. The oxygen used, you get it from the equation of reaction, not the one that was provided. Okay?
Yes.
So it becomes the total volume, which was 212, minus the volume of oxygen that was used, which was 96. The end product is 116 cubic centimeters of oxygen and unused. So is that clear?
Yes, teacher.
Now, what was the volume of the carbon dioxide? Volume of carbon dioxide, because carbon dioxide wasn't used also. What was the volume? Or what is the volume of carbon dioxide from the equation? We are using 2 minutes to get the answer. 2 minutes.
Teacher, could you like pull the paper down so I can see the equation?
It's on the screen.
For what? Who is asking?
Shelly.
Shirley, I want the volume of carbon dioxide because it was also unused. Use the equation here, this one, to determine the volume of carbon dioxide here. Because we used 48 of methane. What is the volume of carbon dioxide? Hmm? Cynthia, what is the volume? Maya, type for me that answer well. I see a curve somewhere, not a number. Okay, that is good. Thank you. I've seen Maya's answer. Shelly. Shelly,
Yes, teacher.
what is the answer? Hmm? Okay, that is good. Joan. Joan, when I call your name, you unmute. You unmute, but you don't disappear. Unmute and talk. Patricia. Have a behavior. You mention the name, they disappear. Patricia. Ha, Patricia, where do you get 44 from?
Just tell me the procedures.
The procedures are up. Compare the volumes. Don't go back to masses. Okay? This is, we are now talking about volumes under Avogadro'S under what?
Gay.
Gay Lusak's law. We are talking about volumes. Don't bring again masses here. When you see things on volumes and they are on gases and what, don't bring volumes here or whatever is here, masses. Use just the ratio and the volume given. That is all. So the volume of oxygen that was unused was 96. Also, the volume of carbon dioxide is 48. I hope who? Patricia. Patricia,
Yes.
I hope you are now attentive. Look at this. Look at this. So our volume of oxygen that was unused was 116. That one remained unused. Also, the one volume of methane produced one volume of carbon dioxide. 48 of methane produced 48 of carbon dioxide. So that was the volume of carbon dioxide that was unused. So if you add the two, it gives us 164. This is the total volume of the two gases unused. Okay. So if you also get the one of the water at the gaseous state and you add it there, it will increase. But now we are not minding about that vapor. We are only concerned about the oxygen and carbon dioxide. So if the question comes, this is the exercise we are going to struggle with for now. This one. So make sure you get, Cynthia, what is the name? You get what? Cynthia is the one who knows these words. You get what? A picture.
Yes, teacher.
You get what? A snap what?
Snapshot.
Oh, a screenshot.
Screen cover.
You get a screen cover and use. Okay. Now let's go back to Avogadro. After looking at this man called Gay-Lussac. Let's now finish up this man called Avogadro. He also based on the same thing, but for him he considered moles. Avogadro. Avogadro. So make sure you do that exercise up, this one. Where you get stuck, inquire. So here they are saying, Avogadro, the law states equal volumes if you remove volumes from, yes? This exercise here, don't you see the exercise on the screen?
Which exercise?
This one under Gay-Lussac's law.
Okay, wait, I check.
Okay. Finished?
Yes.
Finished? Okay. If you have finished, let's look at this man. He says that equal volumes from Avogadro, who say from Gay-Lussac's law, who say they do so in volumes. Equal volumes of gases at the same temperature and pressure contain the same number of molecules. Now, instead of volumes, using volumes at one volume, you go back to molecules or moles in short terms. So Avogadro gives the interpretation of Gay-Lussac's law in terms of molecules of gases. Now he studied it using this, that two volumes, this one was for, who is this one? Gay-Lussac's, that volumes. So for Avogadro interpreted it this way, that two molecules of hydrogen combines with one molecule of oxygen to form two molecules of steam. That is all. Here he said 1 mole of hydrogen combines 1 mole of chlorine to form 2 molecules of hydrogen chloride gas. That is all. This law is quite important because it enables us to change a statement about volumes of gases to the same statement about moles of gases and vice versa. Okay? So the relationship is this one, we shall not take much as this. The relationship between vapor density and molecular whatever, this one is important in that level. When you cross this level, you are going to. But for now, let me not go deep into this one. What is important is this word, what you call the molar gas volume. Now, when you are defining that, or when you are putting your whatever in summary, you define the gas molar volume. Gas molar volume is the volume occupied by 1 mole of a gas. Volume occupied by 1 mole of a gas. Say at different temperatures, there are 2 temperatures they always give, at STP and then at room temperature. Okay? The molar gas volume at STP is 1 mole of a gas is equal to, what's the temperature at standard temperature and pressure? It's 22.4 liters or 22400 cubic centimeters. If it is at room temperature, 1 mole of a gas is equivalent to 24,000 cubic centimeters or 24 liters. So a liter, 1 liter is equal to 1 decimeter cubed, which is the same as 1,000 cubic centimeters. That's the comparison there. So if they tell you to define a gas molar volume is a volume occupied by 1 mole of a gas. And in that state, at STP, it always occupies this, 24. Now, molar concept has started officially now. We looked at molar concept from the start as 1 mole is equivalent to 6.02 times 10 to power 23. What are these? What are these? Particles. Particles or ions or atoms.
Particle.
Yes, which is the same as. Also, 1 mole is the same as the relative atomic number of any given substance or relative molecular mass of any substance or the relative formula mass of any substance. Also, 1 mole is equivalent to, now we are introducing a new one, 24000 cubic centimeters. This is a molar gas volume. At which temperature? Room temperature. It is also equal to
Temperature.
It is also equal to 22400 cubic centimeters. At what? STP.
STP.
So what you get, what 1 mole of a gas can occupy, you know that 1 mole of a gas is also equal to the relative atomic mass of any given substance. So if they say 1 mole of maybe hydrogen. So 1 mole of hydrogen is equivalent to what? What is the weight of hydrogen?
1.
It is 1. So hydrogen can never be 1. So if you are writing hydrogen, is always in the molecule. So it's H2. So 2 grams of hydrogen occupy 2400 cubic centimeters at STP, or 24,000 cubic centimeters at what? Room temperature. If they say iron is 56. So 56 grams of iron occupies 22400 cubic centimeters or 24000 cubic centimeters. This is at room temperature, this is at STP. Have we understood the meaning of the word 1 mole now? Yes?
Yes, teacher.
In an equation, they might ask you for the relative atomic mass of any given substance, but what they have given you is the volume of this. So if they ask for relative atomic mass, get what 22400 cubic centimeters at STP or 24,000 cubic centimeters at room temperature can occupy. Then that's the relative atomic mass in grams of that element. Let's look at examples. That's when you'll understand. Determine the number of moles in the following gaseous volumes at STP. 1.2 decimeters cubed of nitrogen. 1.2 decimeters cubed of nitrogen. They want the number of what? The number of moles, isn't it? Yes? So if they say 1.2 decimeters cubed of nitrogen, you know that from the relationship we had is 1 mole of nitrogen occupies what? Occupies, this one is at STP. At STP is equal to what? At STP, what is the volume of 1 mole of a gas? 22,400 cubic centimeters. But now they have given you the answer in what? In decimeters. You go back to this relationship we wrote here that 1 liter is equal to 1 decimeter cubed, which is the same as 1,000 cubic centimeters. So if you divide this answer by 1,000, you get 20 what? 22.4 decimeters cubed, isn't it? You are not seeing? So if you divide this answer here, 22,400 divide by 1,000, you get what? 22.4 decimeters cubed, or 22.4 liters, isn't it? Yes? So 1 mole of nitrogen occupies 22.4 decimeters cubed. Now go back to the equation. They have given you decimeters cubed. They want the moles. So you write the equation starting with decimeters cubed. So you say 22.4 decimeters cubed of nitrogen are contained in one what? In 1 mole. What about 1 decimeter cubed of nitrogen? It is contained in 1 out of 22.4 moles. Ask yourself, what about 1.2 decimeters cubed of nitrogen? It has 1 out of 22.4 times 1.2 moles. So what is the answer here? Hmm? Hey, where are people gone? They don't have calculators?
Teacher,
Hmm.
got 0.0
5.
Hmm? 0 point?
0.05
Huh?
05
0.5.
05
0.5. So it continues like that. I told you this one, write the answer to how many decimal places? 3. If it is more constant,
So that's not the answer.
it is what?
Teacher,
It's
that's not the
0.05.
it is 35.
Hmm?
0.5. It is 0.053. 53.
53.
5 3. So I remove
Yes.
this. I put 0.053
0.053.
moles. Okay? So that is our answer we have, isn't
Oh
it?
yeah.
Mm. So instead of this, we shall have this one. Now, what is the answer here? I want the answer in 300 cubic centimeters of ammonia. The number of moles in 300 cubic centimeters of ammonia. What do you start with? Start with writing a statement saying 1 mole of ammonia occupies what? Occupies, they have given us the condition is still the same, STP. It is, now they have given an answer in cubic centimeters. Make sure you also write your answer here in cubic centimeters. It's 22,400 cubic centimeters. That is the volume it occupies. They have given you this. You rewrite the statement the other way around and look for the number of moles in ammonia. You have less than 2 minutes to finish the session. So make sure you hurry with the answer. I've seen someone with the answer there. Maya, that is okay. I want to see more 2 answers. We have less than 1 minute now. Okay, peace, that is okay. One more answer. One more answer to go. Cynthia, where's the answer? You are still struggling. Okay, so where we have reached as far as now is concerned, we have at least now we can start up with this paper of the other 200 what questions. Number 1 is there. Which one of the percentage in the number of moles of sulfate in aluminum sulfate? We are left with this one, neutralization reaction, and then this other one here. But now, so far where we have reached, we can calculate numbers in this paper. I will forward, I think, 2 pages of the work, and then I see what I've gone through. For today, we shall stop here.